eppur si muove.
Today, we are undertaking a pretty monumental task. We're diving into the life and work of a man so fundamental to how we view reality that Albert Einstein called him the father of modern physics and, frankly, all modern science.
We are talking, of course, about Galileo Galilei.
Exactly. And our mission today, it's not just historical. We're going to trace his scientific revolution all the way into the space age and look at this surprising 20th century story that demanded the exact same radical blend of rigorous observation and intense personal courage that Galileo needed 4 centuries earlier.
It really is a perfect pairing. I mean, if you want to understand how the scientific revolution completely redefined our world, you have to start with what is maybe the most famous and definitely the most satisfying experiment ever done.
And it wasn't even done by Galileo himself.
No, not at all. It was done by his legacy.
Okay, let's set this up. We're flashing forward to July 1971. We're on the moon, Apollo 15. Commander David Scott is standing on the lunar surface.
Right. And in his hands, he has 2 objects that couldn't be more different on Earth. A geological hammer and a single falcon feather. And he just holds them out at the same height.
And he drops them simultaneously.
And the camera captures it perfectly. On Earth, air resistance would make the feather just sort of float down. But on the moon, you're in a near perfect vacuum.
So there's nothing to slow it down.
Nothing. And they fall together side by side and hit that lunar dust at the exact same moment. It's beautiful.
And what Scott says in that moment, it's just so simple and perfect. He just says, Galileo was right.
You really do have to just pause on that. A principle that Galileo figured out centuries before, that all bodies, no matter their mass, accelerate at the same rate in a vacuum. It was finally visually confirmed in the most distant, most perfect natural laboratory humanity had ever reached.
And it wasn't just Einstein who got how huge this was. Isaac Newton, the man who basically wrote the rule book for classical mechanics.
Right, with the laws of motion, universal gravitation.
He openly said that if he had seen further, it was only because he stood on the shoulders of giants.
Then Galileo was arguably the most crucial giant of them all. He laid the foundation for what Newton would later express in perfect mathematical form. He created the very idea of a new, complete, and finished physics.
So what was that fundamental shift? Because before Galileo, science as we think of it didn't really exist. It was called natural philosophy. And for more than 1,000 years, it was completely dominated by one colossal intellect, Aristotle.
Precisely. Galileo's revolution wasn't just a new idea, it was a total restructuring of methodology. He replaced this reliance on, conceptual dogma and philosophical arguments with a systematic use of observations, experiments, and this is the key, mathematics to describe and predict nature. He didn't just change what we know, he changed how we know things.
So before we can build up Galileo's world, we have to tear down Aristotle's, and his ambition was just staggering. He tried to explain literally everything.
Everything. From the structure of the entire cosmos down to why a flame flickers. And he also defined what counted as correct argumentation, using things like syllogisms to derive conclusions he thought were absolute, unshakable truths.
And his process of knowledge was what they call inductive, right? Moving from specific things you see to universal rules.
Yes, observation was the starting point. But here's the paradox that led to centuries of stagnation. The whole system was easily swayed by flawed human intuition.
Like the most obvious one. The Earth feels stationary, so it must be at the center of the universe.
Exactly that. You watch the sun rise in the east and set in the west, and the most logical, intuitive conclusion is that the sun is moving around a stationary Earth. And once that was established through what they saw as logic, there was no room for empirical doubt. It was just settled.
And that system divided the entire universe into 2 completely separate realms, governed by totally different rules, which is, a huge problem for modern unified physics.
That rigid separation is absolutely key. You had the sublunary world and the superlunary world.
Below the moon and above the moon.
Right. The world sub, or below the moon, was our world. It was the realm of decay, of change, of imperfection. It was made of the 4 elements: earth, water, air, and fire. And everything in this realm was just trying to get to its natural place.
So a rock, which is made of earth, wants to get to the center of the universe, which is earth, so it falls.
Exactly. And fire, being the lightest element, naturally moves upwards, away from the center. Motion here was always temporary and in a straight line, either up or down.
But the second you cross the boundary of the moon's orbit,
everything changed.
Yeah.
Suddenly you're in the perfect, immutable, supralunary world. It was made of a perfect 5th element, ether. And motion there was eternal, divine, and strictly uniform and circular. A perfect circle.
So you couldn't use the same physical laws to describe a falling stone and a circling planet? They were fundamentally different things?
Two different universes, really. And this brings us to how they saw physics and mathematics. Aristotelian science was entirely qualitative, conceptual.
What does that mean exactly? Qualitative.
It means they described the quality of things. Is it hot or cold? Heavy or light? They talked about the essence of things. Mathematics was seen as secondary, almost like a tradesman's tool. It was useful for describing external properties like size or shape, but it could never touch the true nature or essence of an object.
So a learned philosopher would use logic and rhetoric, but doing calculations, that was for craftsmen.
Exactly. And that rigid mindset is perfectly shown in their understanding of motion, which is the very thing Galileo would dismantle. For Aristotle, motion always had to have a continuous cause, unless it was that natural motion of things seeking their place.
So you had natural motion, like a stone falling, and violent motion, like pushing a cart.
Right. And this led to his famous quantitative rule for speed. V is proportional to F divided by R. Speed is proportional to the force you apply and inversely proportional to the resistance of the medium you're moving through.
So to go faster, you need a bigger push or less stuff in your way. Seems reasonable.
It does. But that simple formula had a massive system-defining implication. What happens if you imagine a vacuum? A place where the resistance, R, is zero.
Well, then you're dividing by zero, the speed would have to be infinite.
Infinite. And since infinite speed was conceptually absurd, Aristotle concluded very logically within his own framework that a vacuum was simply impossible. And that piece of pure abstract logic held sway for 1,500 years.
Which is why Galileo's approach had to be so incredibly radical. He wasn't just challenging a bad idea, he was challenging a system that was perfectly internally consistent, even if it was empirically wrong.
And that challenge was social, too. There was this rigid social hierarchy of knowledge, the practical, hands-on, trial-and-error knowledge of, say, an architect or a cannon maker.
The people actually getting things done in the real world.
Right. Their knowledge was considered vastly inferior to the theoretical, principle-based knowledge of the philosopher. They knew how things worked, but the philosophers claimed to know why.
Galileo basically tore down that wall.
He demolished it. He took the practical tools of the engineer, like the telescope, which was originally a military and maritime tool, and he elevated it into an instrument of universal scientific discovery.
This brings us to his direct challenge to authority. He was constantly criticized for challenging dogma, what academics call the ad verecundium argument.
Which is basically just the appeal to authority. You know, it must be true because Aristotle said so.
Yeah.
Galileo's response was brilliant. He insisted that if Aristotle were still alive, he would be horrified by his dogmatic followers.
He had a great quote about that.
He said if Aristotle acted like his followers, he would be a thick-headed, obstinate man with a barbaric soul. Someone who put ancient rules above experience, above the senses, above nature itself.
And this is where it gets so powerful. Galileo understood one fundamental thing. Facts have sufficient power to destroy theories. He didn't just argue, he demonstrated. He created these situations that forced his opponents to look at reality.
And a huge part of his method was consciously limiting his scope, which sounds counterintuitive, but it's brilliant. Aristotle tried to explain all movement in general. Galileo decided to just study one specific measurable thing, uniformly accelerated movement. He wanted to describe how things moved, not get bogged down in the philosophical arguments about their internal essence or why.
And this is the great methodological shift, the birth of modern science, the hypothesis deductive method.
It's a complete break from the old way. First, you propose a hypothesis, but one that's formulated mathematically. Second, you deduce precise empirical consequences from that math. Third, and this is the revolution, you rigorously test those consequences using precise instruments in controlled situations, the experiment.
And fourth, and this is crucial, you refine or throw out the hypothesis if it doesn't match reality.
Yes, and we see that with him. He wasn't afraid of being wrong. He initially thought objects in freefall moved at a constant speed. But when he tested it, the math didn't work. So he revised his hypothesis to what we now know is true, uniformly increasing speed, acceleration.
His dedication to experimentation was just monumental. He'd repeat these experiments literally hundreds of times to get the most accuracy possible.
He was meticulous. And he tied all this rigor to practical application. The perfect example is his proportional compass.
What was that?
It was this complex calculating device he designed. Initially, it was a military tool used to help artillery engineers calculate the exact elevation of a cannon barrel to hit a specific target. It's the perfect blend of pure mathematics, practical application, and theoretical science, all rolled into one. He was the philosopher using the craftsman's tools to find universal knowledge.
Okay, so let's get into the specifics of that. Let's start with the absolute demolition job he performed on the Aristotelian law of falling bodies.
The belief was so simple. The heavier the body, the faster it falls. And it seemed confirmed by everything you saw. A boulder versus a feather. The boulder wins every time. This is the crack in the armor that Galileo decided to exploit.
And he attacked it first not with an experiment, but with pure logic, a thought experiment.
It's just brilliant in its simplicity. Okay, so you take a heavy body, which Aristotle says falls fast. Now you tie it to a lighter body, which falls slow.
Okay.
The combined object now has more total weight than the original heavy body, right? So according to Aristotle's own rule, it should fall even faster.
Wait, but...
Exactly. But at the same time, the lighter body, which falls slower, should act like a drag, a sea anchor, and it should cause the heavier body to fall slower.
So the same object has to fall both faster and slower than the original heavy body at the same time.
It's a direct, inescapable logical contradiction. And since the conclusion is absurd, the initial assumption that speed is proportional to weight has to be false. It's a devastating piece of pure reason, and it established the principle intellectually that in a vacuum, all objects fall at the same rate.
Which then paved the way for that famous and probably apocryphal story of him dropping things from the Leaning Tower of Pisa.
Right, the actual filmed experiment, as we said, had to wait for David Scott on the moon. So the question is, if Galileo didn't have accurate stopwatches, how did he actually measure and confirm his law of acceleration?
He used inclined planes.
He had to. Free fall was just too fast to measure with 17th century technology, so he had to slow down the motion without changing the fundamental property of acceleration. Rolling a smooth brass ball down a gently inclined plane was the perfect way to do that.
And the sources give us this incredible detail about his setup. He had this long wooden board, and he cut a channel in it, and then lined the channel with polished parchment to reduce friction to almost nothing.
It was meticulous engineering for the sake of pure science. And what he discovered was that the distance the ball traveled is proportional to the square of the time it took. That's the relationship that underpins our modern formula, tall $8 becomes.
So he replaced the qualitative guesswork of Aristotle with a precise mathematical law. But the big challenge was time. How did he measure time accurately enough to prove that relationship hundreds of times over?
He talks about using two methods. One was simply his own pulse, which gives you a rough consistency. But the more ingenious method was a specialized water clock. He had a big vessel of water with a tiny tube at the bottom. He'd start the ball rolling and collect the water that flowed out.
And then weigh the water at the end.
Exactly. The weight of the water gave him a remarkably precise and consistent measurement of the elapsed time.
So he could prove that whether the ball rolled for just a quarter of the channel's length or the whole way down, that mathematical proportion distance is proportional to time squared, always held true.
He wrote that he achieved maximum accuracy and that there was no difference even on 1/10 of the time of a pulse beat. That level of detail shows the immense leap from just thinking about things to actually measuring them.
Now let's get to the principle of inertia, because this is the concept that truly killed Aristotelian mechanics. Aristotle said motion always needs a cause. Galileo introduced the radical idea that uniform motion just continues, indefinitely.
It's the bedrock of all classical physics. And he proved it with another beautiful thought experiment with inclined planes. A ball rolls down one plane and then up a second one, and it always tries to get back to the same height it started from, ignoring friction.
Right, and the thought experiment continues by making that second plane, the one it's rolling up, gradually flatter and flatter.
As that second plane gets less steep, the distance the ball has to travel to regain its initial height gets longer and longer. So what happens when you make the plane perfectly horizontal? A flat, frictionless surface.
The distance required to get back to its starting height would become infinite.
Which means the ball would just move constantly at a uniform speed forever.
That sounds exactly like Newton's first law of motion. But the sources point out a subtle but really important error that Galileo made here.
He did. Galileo mistakenly believed that inertial motion was circular, not in a straight line. And this is fascinating because it shows you how even a revolutionary genius can still be constrained by the assumptions of their time.
He was still thinking in terms of a closed spherical universe.
Precisely. The idea of an infinite straight line that just goes on forever didn't really fit into his cosmological model. So for him, circular motion, like the orbit of a planet, seemed like the most natural form of perpetual movement.
So his cosmology was limiting his physics, even while his physics was busy destroying the old cosmology.
Exactly. It took René Descartes and then definitively Isaac Newton to correct that and establish that inertial motion is rectilinear in a straight line. But Galileo gave us the conceptual breakthrough. Motion persists without a cause. That was the giant shoulder Newton stood on.
And finally, we have the concept of the relativity of motion, which was so essential for defending Copernicus. You know, if the Earth is spinning and flying through space, why don't we all feel it and fly off?
The famous shift cabin analogy from his dialogues is the perfect answer. He says, imagine you are in a windowless cabin on a ship that's moving at a perfectly smooth, uniform speed. You can't tell if the ship is moving or at rest just by observing things inside the cabin.
A drop of water will fall straight down, a fly will buzz around normally.
A stone you throw will land exactly where you'd expect it to. The state of being at rest and the state of being in uniform motion are equivalent or relative within that closed system.
So this immediately dismantled that classic argument against a moving Earth, that if you drop a rock from a tower, it should land far behind the tower because the Earth moved underneath it.
Right. Galileo explained that the rock, the tower, you, the air, everything shares the same system of reference. You're all moving with the Earth, so that shared movement becomes invisible and undetectable to you.
And what's amazing is how far ahead of his time this was. Galileo's idea of relativity was perfectly accurate for everyday speeds, but it was Albert Einstein who later showed that those rules break down near the speed of light, and that the speed of light itself is the one absolute constant. Let's move from mechanics on Earth to the cosmos, because the old geocentric model, the Ptolemaic model, was crumbling under its own weight.
It really was. And all that complexity was driven by this desperate struggle to save an ancient dogma from Plato and Pythagoras, that celestial bodies have to move in perfect circles at a uniform speed, because the circle was a divine, perfect shape.
But observation just didn't match that. You had planets that seemed to change in brightness, and then you had that really weird looping motion, retrograde motion.
Absolutely. And to keep the Earth at the center while explaining these anomalies, the models became absurdly complicated. First, they had to introduce epicycles.
So the planet moves in a little circle,
whose center moves on a bigger circle, the deferent, which moves around the Earth. Then, when that wasn't enough, they added eccentrics, which meant the center of the main orbits wasn't even the Earth anymore.
And the worst fudge of all was the equant.
The equant was a total mathematical cheat. It was an imaginary point off to the side from which the planet's movement appeared to be uniform. So they sacrificed the Earth's central position and the principle of uniform circular motion just to save the appearances.
So when Copernicus came along, his motivation wasn't necessarily new data, it was just aesthetic disgust.
That's a great way to put it. He reviewed Ptolemy's work and famously called it a monster, a collection of perfectly drawn parts that just didn't fit together into one coherent body. He wanted simplicity and harmony.
And he found it by putting the sun at the center.
Right. By doing that, he could still use uniform circular motion, but suddenly retrograde motion wasn't a mystery anymore. It was just a simple consequence of a faster-moving inner planet, like Earth, overtaking a slower-moving outer planet, like Mars.
So Copernicus gave us a much simpler, cleaner mathematical hypothesis. But it was Galileo and his telescope that provided the hard, irrefutable evidence.
Galileo was a master of technology. He didn't invent the telescope. That was probably Hans Lippershey, but he dramatically improved it, got it up to a 30x magnification, and most importantly, he was the first person to systematically point it at the heavens and publish what he saw.
And his first observations immediately proved that the heavens were not perfect, not immutable, not made of some magical ether.
He pointed it at the moon and drew these incredibly detailed images of a rough, cratered surface with mountains and valleys. He even estimated the height of the lunar mountains by measuring their shadows. This completely contradicted the dogma of the moon being a perfect, smooth sphere.
Then he looked at the sun.
Using a projection method to avoid blinding himself, he saw sunspots. These spots moved and changed, which proved two things. One, the sun was not a perfect, unblemished orb, and two, it rotated. The idea of a flawed, rotating sun was just heretical to the Aristotelians.
And the sheer scale of the universe just exploded overnight.
The telescope just opened the floodgates. He saw hundreds of stars and constellations like Orion that had never been seen before. He He showed that things Ptolemy had called nebulas were actually vast clusters of distant stars. He was hinting at a much, much larger universe, though he was very careful not to talk about an infinite one.
Because of Giordano Bruno.
Because of Bruno, who had been burned at the stake just a decade earlier for that very idea. Galileo was pushing the boundaries, but he knew where the edge was.
But the true, undeniable proofs of heliocentrism were twofold. First came the moons of Jupiter.
In 1610, he discovers 4 points of light orbiting Jupiter, what we now call the Galilean satellites, Io, Europa, Ganymede, and Callisto. He watched them night after night and saw that they were clearly revolving around Jupiter, not the Earth.
Which was direct empirical proof that not everything in the universe revolved around us.
It dethroned the Earth as the sole center of motion. It was a miniature solar system that everyone could see, proving the concept was possible.
But the true checkmate observation was the phases of Venus.
This was the killer blow. Galileo observed Venus over many months and saw that it went through a full set of phases, just like our moon crescent, half, gibbous, and full.
And in the old Ptolemaic model where Venus is stuck between the Earth and the Sun, that's impossible.
It's geometrically impossible. In that model, you should only ever see the crescent phase of Venus. To see a full Venus, it has to be on the far side of the Sun from us.
Which can only happen if Venus orbits the Sun.
It was the absolute, undeniable, geometric proof. No amount of theological argument or Aristotelian logic could explain away the phases of Venus. The old model was dead.
It's amazing to think that modern missions have confirmed the scale of what he found. NASA probes have shown us Io's incredible volcanoes and Europa's hidden ocean. His little points of light were actually complex worlds.
His findings were just the first step, but it was the step that changed everything.
So Galileo had the facts, but he ran headlong into the entrenched power of the church. And the core of the conflict, it wasn't really just science versus religion. It was about who had the authority to interpret reality.
That's exactly it. The church was actually okay with the Copernican system as long as it was treated as a mathematical tool or a speculative hypothesis, something you could use for calculations.
But not as a true picture of the world.
Absolutely not. They couldn't accept it as naturalism, as how the world actually is, because that directly contradicted certain literal interpretations of Scripture, and more importantly, it undermined the entire intellectual framework of Aristotle that the church had built its theology upon.
And Galileo tried to argue for separation of these two domains. He famously wrote that the Holy Spirit's intention is to teach us how to get to heaven, not how heaven is arranged.
He was arguing for what we now call non-overlapping magisteria. He said theology deals with faith and morals, and science deals with nature and observable facts. The Bible, he argued, often uses metaphorical language for the common person. It shouldn't be used as a science textbook to constrain what we can plainly see.
But that was seen as a direct challenge to the church's exclusive authority to interpret Scripture.
It was. And when he published his masterpiece, the Dialogues concerning the two chief world systems in 1632, he pushed way too far.
The structure of the book itself was a provocation.
It was. It's a conversation between three characters. You have Salviati, who argues for Galileo's position. You have Sagredo, the impartial, open-minded observer. And then you have Simplicio, the dogmatic Aristotelian.
And Simplicio, whose arguments are constantly demolished, was seen as a caricature of Galileo's opponents, and even of Pope Urban VIII himself.
That was the fatal error. The book led directly to his trial and condemnation.
The charge was that he had violated the ban from 1616 on teaching the Copernican system as fact.
The process was severe. A confession was extracted from him under threat of torture. He was deemed seriously suspected of heresy.
And on June 22, 1633, the old man was forced to get on his knees and read a public retraction denying that the earth moves. His works were all put on the index of forbidden books, and he was sentenced to lifetime imprisonment, which was later changed to lifelong house arrest.
And it's important to note, just to keep things balanced, that Galileo did get one big scientific thing wrong. He failed to find a direct physical proof of the Earth's motion, and he mistakenly believed that the tides were caused by the sloshing of the oceans as the Earth rotated and revolved.
He completely missed the gravitational pull of the moon and sun.
He did. He was convinced he had the proof, and he was wrong. It shows that even the greatest minds can be led astray by a favorite hypothesis.
Yet, even stripped of his freedom, growing blind under house arrest, the fire didn't go out. It was then that he wrote what is arguably his most important work on mechanics, the discourses and mathematical demonstrations relating to two new sciences.
That book, which had to be smuggled out of Italy and was published in the Netherlands, laid the absolute foundation for all of classical physics. It detailed his findings on projectile motion, proving a cannonball follows a parabola, and codified his laws of motion. It was the beginning of the entire field of mechanics.
And his mind just kept going. He foresaw so much. He nearly discovered the theory of probability. He speculated on the aberration of light. He predicted unseen planets beyond Saturn. He even tried to experimentally measure the speed of light. His legacy is just the ultimate triumph of rigorous method over authoritarian dogma. Okay, now let's make that crucial jump. A huge shift forward in time, from the scientist under house arrest to the mid-20th century. We're going to look at how Galileo's spirit was absolutely necessary, not just to get to the moon, but to deal with what humanity found there. This brings us to the high-stakes, private race to the moon led by Dr. Donald Cargraves.
This is such a fantastic modern echo. It takes the scientific method out of the lab and puts it in a situation where the stakes are life and death. Dr. Cargraves is a Nobel-nominated nuclear scientist, and he applies that pure experimental spirit to space travel.
And his motivation is twofold, right? The freedom of science, but also a patriotic desire for the U.S. to lead in space.
He's a patriot, but his ultimate allegiance is to scientific truth, wherever it comes from. And he's facing huge constraints, financial and logistical, which forces him to make some really unusual choices.
Like recruiting 3 teenagers for his crew.
Exactly. Art, Ross, and Maury. He calls them sufficiently reckless for the mission. And the team itself is a metaphor for modern interdisciplinary science. Art is the photography and radio guy, Ross is the chemist and fuel expert, and Maury is the astronomer and navigator using spherical trigonometry for their lunar alignment.
So they're blending theoretical knowledge and practical skills, even making their own instruments in a school workshop.
It's pure Galilean spirit. And the resources they pull together are just incredible. They get a surplus transatlantic rocket, the B-17, basically for the price of scrap metal.
And for fuel?
Cargraves uses his connections to get thorium from the UN Atomic Energy Commission for his custom atomic engines. And because it's such a high-risk project, he institutes these incredibly strict safety protocols. This is the modern application of Galileo's rigor.
Constant use of film badges, electroscopes, mandatory blood tests.
And he warns the boys that violating the laws of nature means they're off the project instantly. It's the scientific method codified as a survival protocol.
So let's follow them on the flight of the Galilei, a fast 46-hour journey to the moon.
And right away, the physics of the trip challenges their assumptions. Ross, the chemistry expert, questions their speed. They're only moving at 300 miles per hour, way less than the 7 miles per second he thought was needed for escape velocity.
Why is that a misconception? How did they escape Earth's gravity at such a relatively low speed?
It comes down to orbital mechanics. The 7 miles per second figure is what you need for a direct ballistic launch to escape gravity with no more thrust. But they're smarter than that. They use their main engines to get to a high initial altitude, and then they coast into a transfer orbit and elliptical path that carries them toward the moving moon.
So they're constantly under the influence of the Earth, Moon, and Sun, and their cyber pilot, Joe, is constantly recalculating their trajectory based on those relative movements.
It's Galileo's principle of relativity playing out on a cosmic scale, and the flight itself becomes a mobile classroom. Cargraves is drilling them on geometry and physics while they're performing these complex orbital maneuvers.
And then comes the moment they transition to free flight and turn the ship around. The ultimate perspective shift.
Right. The sources describe the Earth as this massive, brightly shining crescent, 16 times larger than the moon appears from Earth. You can see the polar caps gleaming, the green of the seas, and then the dark side, faintly lit by the moon behind them.
And the lights of civilization.
Yeah. They see these 3 bright clustered lights, London, Paris, Berlin, and then one single distinct beacon on the edge of the Atlantic, Broadway in New York City. It's this moment of profound awe, realizing the Earth is just another sphere in space.
But Cargraves keeps them grounded in scientific reality. He issues a vital safety warning.
He insists they use dark glasses and filters against the raw, unfiltered solar radiation. It's the brightest sun human eyes have ever seen. He warns them about cosmic rays, even making a wry joke about the risk of mutation. It grounds that poetic moment in real, calculated risk.
So they reach the moon, orbit the far side, which Ross finds disappointingly similar to the near side. And then comes the twist.
The twist that turns a scientific exploration into a thriller. As they're preparing to land, they get a radio transmission. It's from a Commander James Brown, who claims to be leading the first lunar expedition. They've been anticipated.
And this is where all goes wrong.
As they're descending, a second rocket appears, silent in the vacuum. It fires. and the Galilei is just torn apart by a soundless explosion. Their ship is a wreck. The mission instantly shifts from science to survival, and it demands the same kind of courage Galileo needed against the Inquisition.
They managed to get close to the attacker's landing site and capture a pilot, only to find out the horrifying truth.
A secret Nazi base. Operating in total secrecy from the moon, with atomic rockets named Wotan and Thor, planning to wage atomic war on an unsuspecting Earth.
The captured lunar vehicle has German words for oxygen and alcohol stenciled on it. The captured pilot, von Hartwig, reveals their goal: to bomb the Earth until the helpless nations surrender.
And the scientific spirit of the crew, their dedication to logic and protocol, is immediately put to the test. Cargraves, who's injured and in shock, momentarily breaks.
He loses his nerve. He says the club is closed. The flight is canceled.
He wants to just go into survival mode. It's a pivotal moment because it shows the leader's human fragility when faced with an unimaginable threat.
But the boys, who've been steeped in the rigorous logic of the scientific method by Cargraves himself, they push back.
And this is the deep insight of the story. They use Cargraves' own rules against him. He established that the team medic determines fitness for duty. So Art, the medic, places the doctor on the sick list because he's clearly in a state of confusion. And according to their protocol, that puts Maury in command.
And Ross challenges Cargraves directly, using pure logic. He says the inherent risk of their atomic spaceflight was always greater than dealing with this new, tangible threat on the ground.
It's an incredible moment. Protocol and reason prevail over fear and the emotional state of their senior authority figure. The scientific method saves the mission, not seniority.
Their final act is this blend of scientific courage and moral necessity. They decide they have to destroy the Nazi base, and they discover that the rocket they captured, the Wotan, was actually an American-built ship, the Detroit City, that had been acquired through secret channels.
Cargraves, back in command, forces the captured pilot, von Hartwig, to fly them out in that ship. And the critical final step, just like Galileo needing to get his discourses published, is to share the knowledge.
Art gets on the radio and transmits an urgent message to a UN patrol in Australia. They successfully warn the world, ensuring that the empirical knowledge they gained, the existence of the base, is shared, stopping the authoritarian plan in its tracks. What really stands out to me is that continuity. From Galileo in the 17th century to Cargraves and the boys in the 20th, it's the exact same principle at work.
It is. Galileo established the method. Courageous observation, rigorous mathematics, empirical testing, all used to challenge an entrenched authority. And that exact same spirit was what the crew of the Galilei needed to succeed.
The boys, who were trained to revere objective truth and measurement, they used their intellect and their adherence to protocol to win against this secretive authoritarian force. Galileo's personal struggle, being forced to recant his findings, it's echoed by the mortal danger this crew faced to make sure their finding that the Earth was in grave danger was heard and accepted as fact.
And in the end, Galileo's persecuted work, the Discourses, became the bedrock for Newton's laws. The very laws of mechanics that made the Galilei mission even possible centuries later. It's the triumph of the method over the personal fate of the scientist.
So what does this all mean for you? The sources show us that Galileo was often wrong about his specific hypotheses. He was wrong about the tides, he was wrong about circular inertia, but he was fundamentally right in his method. A testable hypothesis plus math plus a rigorous experiment.
And Dr. Cargraves' team also made technical mistakes. But the mission succeeded because they embodied that critical thinking. They were able to question assumptions and adapt instantly to new facts, like the sudden discovery of a hostile military base on the moon. True knowledge requires challenging our deepest held beliefs. It means trusting the data and the protocol, even when authority or charisma fails.
So the question for you is this. If knowledge requires testing your assumptions, what core beliefs or processes in your own life or work are you holding on to based only on authority? And what small, low-risk experiment can you design today to actually test them, just like Galileo tested the speed of falling objects?
Until next time, keep digging deeper.
Join us and keep your curiosity well fed. Who knows? The next video might be exactly what you didn't know you needed.